lesson 8, Unit 7, lesson 8. So we're just putting it together now. So our first chunk of Unit 7 was solving. Okay, that's the quiz you were doing. Okay, that can be done a lot of different ways. You can solve by factoring. You can solve by inverse sine, inverse cosine. You can solve by your calculator. So your quiz is a combination of those things. But now we're going to combine it with the solving and the identities, which is the second part. Okay, so we had the solving, identities, the last lesson, solving with identities. Okay, so let's look at that. These are more complex problems. This is lesson 8, so it is the harder ones, you could say. So let's just pause for a second. And 2 cosine squared x plus 3 sine x. What makes that difficult when you first look at it? What makes it hard to solve? Go ahead, Hannah. What? Could. There's nothing in common. Okay, you have cosines and sines. Good. Anybody else? That's pretty much it. So, trick question. Okay, so yes. Cosines and sines are different. This is where we need our identities. Okay? Is there any identity for sine x? Anything to do with sine x in your formula sheet that you can change sine x to something else? Sine x is pretty much bare bones. How about cosine squared? Yes. Okay? Cosine squared, again, the cosine squared, if anything, guys, like and you guys aren't good at it yet, and I need you to get good at it soon, we got to have this one down. And the variations of that one. So cosine squared x can also be written as 1 minus sine squared x. Come on. Okay? Why that's helpful is because I can change this cos squared x to a thing with just sine squared x's, and now I'm more comfortable. That's why that helps me. Okay? So what I'm going to do is this 2 still here. I put the brackets, and I put 1 minus sine squared x in for cos. I put plus 3 sine x, and then we're put equal to 0. We're just going to distribute the 2. Okay. This one, I wish they would have done this in the first one, just because it's one little thing that's probably going to bug you. But I hate factoring things with a negative leading coefficient. This one has a negative leading coefficient. What can I do to change that? Add it to the other side, good. Or I can just pull a negative 1 out. It doesn't matter what you do. Okay? I'm just going to essentially, in my mind, I'm moving it to the other side. So this means everything flips their sign. So I'm just going to write as 2 sine squared x minus 3 sine x minus 2. What do we do here? It's factoring. Right. So if you're not seeing it, picture it like this. That's how I want you to picture it. 2x squared minus 3x minus 2. That's what it is. It just has signs for x's. Okay? So yes, we are going to factor it. So we're going to go 2 times negative 2 is negative 4. Factors of negative 4 that give me negative 3 is negative 4 and 1. Sorry. I'm doing decomposition. So how are you going to write it? You're going to write it as 2 sine squared x minus 4 sine x plus sine x plus 1. Oh, it's not plus 1. Thanks. Minus 2. I was looking at this one here. Minus 2. Thank you. I was like, that's not going to work. All right. We group, and we pull out common factors. What's the common factors of the first bracket? 2 sine x. So that becomes sine x minus 2. Second one already is sine x minus 2. So then we're picturing we're pulling out a 1. It's just positive because we don't want to flip the sign. Yeah, because we already have that matched, right? Okay, I'm going to go ahead and write on the right side. We'll restart for the next one. But you're done for the factoring. So those are equal to 0. So what do we want? Yeah, we want the zeros. So sine x equal to e negative 1/2. Good. Now, does sine x ever equal to? Does the graph of sine x ever equal to? This one's not possible. You can cross that off. Sine x, because the regular graph of sine x just goes 1 to -1. That's the sine of x. We know what that is. It goes 1 to -1. Can a sine x be stretched in amplitude? Well, of course it can. But do we have that? No, we have sine x equals 2. That's not possible, so we cross those off. We've done that a couple times. I think before last it was a 3, I think. Couldn't be a 3. Sine x -1/2, we like that. We know where that's at, right? Where's that? It's right here. There and there. Those little sliver cuts. The first ones past the x-axis, which are? Good. 7 and 11 pi over 6 are your solutions to this equation. That's your answer. Okay? Questions or concerns with that one? Okay. Those of you guys that are gone on Friday, B is going to really be difficult for you. We did that, the sum and difference, right? About 5 more seconds, and I'm going to take the writing off. So if you need it. Okay. So this one here, the giveaway is they're written in something plus and something minus. We did a sum difference formula. So you should, when you visualize this or when you see this on an exam, your mind's like, oh, that's cos A plus B, and that's cos A minus B. I have an identity for that. I have a formula for that. Okay, use it. Okay, so this right here is A, this is B, this is A, this is B. Cosine's pattern goes like so. Cosine's a little bit different. It goes cos, cos, sine, sine. So it goes cos of A, so x, cos of B, pi over 6, minus, for the plus it's a minus, it's opposite, minus sine of x, sine of pi over 6. I'll tell you why this is helpful. Then we're going to go minus the group, because you're minusing another cos difference formula, and then it's cos, cos, plus. And you're going to see why this is helpful. If you don't know where I just got that, if you look in the back of your book, it says sine of A plus B. That's the identity for the sum difference formulas. If you're confused from here to here, I'm sorry, you're just reading a formula. Yes, it's equal to 1. I'm just running out of room. Equal to 1. Yep. Okay. So what's helpful with this is that we know what that value is, what that value is, what that value is, and what that value is. And so we're going to do those. Okay? So what's cos of pi over 6? Root 3 over 2. So if cos x, root 3 over 2 there. Sine of pi over 6. 1/2. Now minus a cos, again, pi over 6, so it's a minus a cos x, root 3 over 2. And then it's going to be, again, a minus, a plus is a minus sine x of 1/2. So I distribute the negative, and I got the values for the pi over 6's there. This is where things kind of, I don't know, that aha moment a little bit. Why is that helping me? Oh, no, not really. Not in this one. You could. It could help you. I would group more if I saw some squares and stuff that I was trying to factor. I don't see any squares here. So these are actually all like the cosines are like terms and the sines are like terms. If you want to put them close, you can. But I see, exactly. Jake just said it. You can cancel. Cos x of root 3 over 2 minus cos x of root 3 over 2. See ya later. I have a positive one and a negative one. In that case, it doesn't matter what the x is, right? And then here it's even better. I like this too. I have a negative sine x of 1/2, another negative sine x of 1/2. So what do I have? I have 2 of them, but what's 2 halves? -1. So this becomes negative sine x equals 1. Now we're really comfortable. -1/2 minus 1/2 is -1. So I have -1 sine x. Great, like terms. The sine x's were like terms. So I have a Remember, this is not, maybe this is hard to see, but this 1/2 is not part of the sine of x at all. So it's 1/2 sine of x, a negative, so negative 1/2 sine of x, 1/2 negative sine of x. So 2 negative 1/2 make a negative whole equals 1. So we're essentially, all we're trying to figure out is when is sine negative 1? Where is sine negative 1? You are done. 3 pi over 2. 3 pi over 2 is the solution. Yeah, not too bad, right? Now, it's not too bad, right, Jake? I think you're making a good point. But this looks messy. Right. It's a lot of, just a lot of writing. And, when you use calculus, it's going to be worse in terms of that kind of stuff. But, yeah. Yep, Maddie? Cos x. Yes, because we got this actual value. The value of cos 3x is root 3 over 2, so we replaced it. So we're not multiplying the coses, no. And you only could multiply the coses if you knew they were the same value, because they have to have, for this, cos x times cos x is cos squared x. But if I change this to an xy, they're now different argument, different, that log, I shouldn't say argument because logarithms, but they're different coses of something, so that wouldn't be squared anymore. They have to have the same something, just call it squared. Does that make sense? So these ones have pi over 6 and x. Great question. Great question for foundation there. Okay, anything else? All right, let's do example 2, and then we get a little bit difficult in terms of its investigation, but this one's not too bad. Okay, so consider the equation 4 minus sine of x equals cos 2x. So it says, which of the 3 identities for cos 2x would be the most efficient replacement for solving this equation? So again, the problem is I have sines and coses. So why don't you look in your back of your book there and see which cos of 2x would you like to use? The cos of 2a's, there's 3 of them. That's one of them. Do we want to use that one? It's the only one you see? Oh, I thought there was 3 of them listed. That's okay. So, the sine 2a. Okay. So what's it say? Cos 2a says, it says cos squared x minus sine squared x. Okay, that's fine. Because we're comfortable. So that's helpful because it gives us cos squared sine squared. And anytime we see a cos squared sine squared, we can write it with the other one. So we clearly want things in terms of sine because of that sign there. So I can change this cos to another sign by putting 1 minus sine squared. Like that, see? I replace the cos with a 1 minus sine, so then what do I have? I have 1 minus 2 sine squared x. Right. So this is where we're at. And then I'll pause and take questions. This is where we're at right now. Okay, so yeah, we combine that, so it's minus 2 of them. We now have everything in sine. I'm going to move everything to the left so I get a positive 2 sine squared so I can factor again. Add that over. Minus sine x. Minus the 1 to the 4, so minus 3. Just move this stuff on the right to the left. Add the 2 sine squared x, minus the 1 to 4. The 7x was there. Okay. Yep. Do you understand where the 2 sine squared x came from?
Yes. I just don't understand how you moved it over.
Just add over. Plus, minus. That's a plus 3. Yep, there you go. That's the problem.
Where did the 2 come from?
Okay, let me get the 2 sine x squared first. Right here, Maddie. 1 minus sine squared x minus another sine squared x. So these are like terms. There's 2 of them. This is just the same thing as, that's the same thing as like an x squared and x squared. It's 2x squareds. Okay? Yeah. All right, next question, Zoe. And so, yeah, this is a positive 3. Sorry. You minus the 1, minus the 1. 4 minus 1 is 3. The 7 stays because we didn't move that. And then I added this over, so now it's positive. So that's everything that's on the left now. So now we're looking at 2 times 3, like Natalie said. 2 times 3 is 6. Factors of 6 to get you negative 7, negative 1, negative 6. And now we're ready to factor. 2 sine squared x. Let's go minus sine x, minus 6 sine x. Remember, it doesn't matter the order you put those in. You can go either order you want. And we're going to group, and we're going to factor.
When they say general solution, that's the thing where it's like
Plus n. Yeah. 2 pi n or whatever. Yep. Okay, pull a sine out of the first one. I get 2 sine x minus 1. Pull a negative 3 out of the second one. I get 2 sine x minus 1. We have it factored now. All right. Whole thing equals 0, right? What do we know about that one? Sine x equals 3. Can't do that one. No good. Sine x never 3. Just like we said in the last problem. Previous one where it was 2. Other sine x needs to be 1/2. Where is sine x 1/2? Pi over 6 and 5 pi over 6. Now, I'll pause now. Let's see if everybody's where we're at for the pi over 6s, and it's fine. Questions are good. Negative 1. I pull the sine x out. The 6? Factors of 6 that give me negative 7. Negative 1 and negative 6 gets me a negative 7. Negative 1 times negative 6 is positive 6. Here? Yeah? Yeah, that's fine. Yep, yep. Okay, so what she asked is, can you sub the signs out for x's and factor it? Sure. Yeah. Yeah, you could write this right here. This is the second line. 2x squared minus 7x plus 3, and you could factor it and then put the signs back for x. It's fine. Yeah, people like that's a little cleaner. That's fine. Okay, so we got it. Pi over 6, 5 pi over 6. It does say general solution, though. Okay, so it happens every pi over 6 plus 2 pi n, every pi over 6 plus 2 pi n, and then NEI for both. Remember, it's 2 pi because every time you do a 2 pi, it's going to be around on that same spot because we're talking about radians. Yep. Yeah, that might be good. Okay. Any questions on that before we get into this a little bit more difficult thing here? More difficult, yeah, I know. This seemed pretty hard. It is pretty hard. This next part's not hard. I think just the reasoning gets a little tough. That's okay. All right, let's keep going then. All right, so we're investigating. So let's talk about the point that we're doing. We're investigating the validity of dividing by a variable expression. Okay, the validity of like how it stays consistent. So we're going to do 2 problems here. We're looking at somebody's work, and we're going to finish it. So we're looking at sine x equals cos x, and then sine of 2x equals cos x. Okay, so 2 different problems. We're staying on 0 to 2 pi, so we're talking about radians. Okay, so if I solve this, okay, what they did was they divided cos x over. Okay, why do they do that? Because then sine x over cosine x is tangent x. What's cos x over cos x? Because subtracting wouldn't help you really, because you like sine x minus cosine x isn't an identity of anything that gives me a value. Yeah, but the reason they did do it is because they divide the cosine of x, we get the value of 1, and we like the value of 1 for our thing. But I didn't think about why they didn't subtract. But the thing, though, too, to think about it, yeah, the thing that's interesting here, too, is this is really just telling you when is sine equal to cosine, and we should know that. sine equals cosine at 45, root 2 over 2, root 2 over 2, and at 225, negative root 2 over 2, negative root 2 over 2. That's when sine and cos are equal, x and y, right? And that's what this tells us, because tangent is 1 at pi over 4 and 5 pi over 4. So that's the solutions to that problem. So there's a couple ways you could have thought about that, is the point. I just don't think subtracting would have really helped you. Well, I mean, I guess it could help you a little bit, Natalie. If you can see that sine x minus cosine x equals 0, you want to know when is sine and cos the same. If you can say, oh, that's pi over 4, 5 pi over 4, that's fine. But when you do it like this, you actually kind of get the actual ratio. It's a little bit easier to see just in this case. Okay, so the second one says sine of 2x equals cosine x. So what they did was, we don't like the 2 of x here, but we do know the 2 of x. What's that do to the sine graph? Let's think about it for a second. What's that do to the sine graph? It compresses. It means it happened more often. So that means it's probably going to have more answers, right? Because this right here was just single sine and cosine curve. We're going to look at the graphs in a second. This is sine of 2x. So it compresses the sine graph, so it's happening twice as fast. Okay? So, but if we solve this the same way they just did, they divide cos x, they divide cos x, they cancel. Okay? You get 2 sine x equals 1. And now we're really solving for sine x equals 1/2. Good. So when is sine x 1/2? We've already done this one today. It's at pi over 6 and 5 pi over 6. Now, what's the problem with this? We only got 2 solutions, but how many were we expecting? Yeah, exactly. We're expecting 4. Why are we expecting 4? Because the sine curve's happening twice as fast. So that intersection with cosine is going to happen in twice as many spots. Okay? So this isn't completely valid, and we're going to show why. Okay? We're going to show why here in a second. Let's go and take this to the calculator. Okay? You can go and take it there with you. Here's the window you're using. 0 to pi, pi over 6, one we usually use. Negative 2 to 2 with 1 for your scale. And this is the graphs you're going to get. Okay? I will go ahead and pause the video, let you guys get there. Okay. Okay. So let's just kind of talk about the first one. So the first one, here's an intersection spot, and here's the intersection spot. Those spots were as expected. They were the pi over 4 and 5 pi over 4. So this one had no issues. But as we talked about, on the algebraic one for the second part, we thought we were going to have 4 answers, so we got 2. Okay? And this spot and this spot are those answers that we got. Can anybody take a guess to why this one didn't show up or this one? Good, they're x-intercepts. Good point. What do we cancel? We canceled cos. We divided and canceled cos. So what happened was when cosine is 0 actually works, because when you put that into the left-hand side before you try to solve it, they're equal. And so by dividing, we ruined the validity because cosine of x was disregarded because we canceled the cosine. That's what happened. So we canceled the cosine, which eliminated 2 of our answers. So here's the short story. I'm going to say it as simple as I can. When you are solving these, if you divide something, you need to make sure that that something is not a solution when it's 0. Okay? So cosine of x, when cos is 0, is an answer to this problem. This is why. Look up here. See right here? If cos is 0, what's 0 times this? And what's 0 here? 0 equals 0. So that's a true solution. Okay? But when we divide this off, that goes away. We just have 2 sine x equals 1 now. So that you essentially get rid of an answer by dividing the cos. So when you divide a cos or a sine, guys, make sure that you think about what you divided as a 0. The reason it didn't bother us here is because cos at 0 wasn't a solution. Okay? That was the difference. So these 2 were the ones we got. That's pi over 6. That's 5 pi over 6. So those ones are good. The new ones we picked up is when cosine is 0. So when's cosine 0, guys? Gals. When's cosine 0? Top, bottom. Pi over 2, 3 pi over 2. Those are the 2 solutions that were missed algebraically because of the cancel. You can graph it, or just, like I said, when you divide a cosine and cancel it, you need to be like, I need to make sure that's not a solution. Okay? You need to make sure that cosine of x being 0 isn't a solution. In this case, it was. Okay, so what it says here says, does the algebraic solution in part 1 agree with the graphical? Yes. Does the algebraic solution agree with the graphical solution in part B? No, due to the canceling of cosine. Okay, now we're just summarizing, guys, and we're almost done here. So it says the algebraic solution in A is correct, but the algebraic solution in part 2 is not complete. This is because the division by cosine of x is valid in A, but not in B, or part 2. I wish they just decide if they want A or B. Okay, but part 2. Under what circumstances is in general, is division by cosine of x not valid? When the solution is possible for cos of x being 0. Okay? Okay, when cos of x equals 0 is a solution, it's not valid. So that's what I was saying. When you divide a trig over, you got to make sure that it being a 0 is not an answer. Okay, they're going to finish it up here at the next page, and then we're going to go to our last example, and then we'll be done. Any questions? So just in general, like, again, I know this is a difficult lesson. I know this is a little bit abstract thinking, but the idea with that, what they're trying to show you is that there's 2 answers that you miss because you simply cancel it and think about that being a possibility. Okay? So just make sure that when you're doing that, that you look for that. Natalie, if you want to just check your work with the calculator and see that you're missing one, that works too. If that's just making sure that you know algebraic could have some holes, that's fine if you want to think about it that way too. So here it is. So since division by a variable is not valid if the variable expression can equal 0, we need to determine whether cos of x can equal 0 in solving the equations. So sin x equals cos x or sin 2x equals cos x. Consider a solution of cos x being 0, for example, of pi over 2. So they're saying is, we know that cos of x equals 0 at pi over 2. Well, if I plug pi over 2 into the first equation, what's sine of pi over 2? 1. What's cosine of pi over 2? That's why that one worked. It was okay. Pi over 2 was not a solution that worked in the original. But now look at this one. This is where it gets really interesting. And remember on your test, how far apart is cosine and sine's graph? It's pi over 2 apart. You can slide over pi over 2 and they'd be on top of each other, right? Look at this. What's 2 times pi over 2? Just pi, right? 2 times pi over 2 is just pi. What's sine at pi? 0. What's cosine at pi over 2? So it works left and right on the value of when cosine is 0. Okay, so that's how you're checking. That's what I'm telling you guys. Okay?
So could you like graph it?
Yeah.
And then check all your answers in the equation?
Sure. You can graph it and check. Sure. That's fine. Yeah. Okay, so that's what they're talking about the pi over 2. They're using pi over 2 to show you the left side, right side type of thing. If x equals pi over 2 is not a solution to either equation, the step in which the student divides the cosine of x is valid. So when I plugged pi into the first one, see how they weren't equal? It's valid to do that, to eliminate the cosine there, divide it over. But if they are equal, then it's not valid to divide it and still get all your answers. Okay? So that's essentially what they're saying. So the work in this investigation, the student's approach to solving sine of 2x cosine x is not valid. Determine the correct solution. Use the double angle identity for sine 2x. So the double angle can help us get all the answers is the cool part. Probably I'm the one that thinks it's cool, but that's true. It's fine. So watch. Take your double angle for sine 2x. Correct me if I'm wrong, but I'm pretty sure it's sine, what is it? Oh no, it's 2 sine x cosine x, right? Is that what we're writing? Yeah. And this is actually, you're going to like this, Natalie, because this is what you were saying. So, close. Not quite. So we divided last time. That was the problem, right? And so, Natalie, yes, we subtract now, Natalie. That's actually kind of cool that you said that earlier. I didn't think about that. Now, why is that helpful? Because it even gets, again, I'm being nerdy, but it even gets cooler. What do they both have in common? Pull the cos out. Aha. So we want the answers of cosine being 0 and sine being 1/2. So that part that you canceled, remember we got sine of being 1/2 the first time, but we were missing the what? The when the cosine is 0, and now we have both of those. So now I have all 4 solutions here. I'm looking, answers are when cosine is 0, so 3 pi over 2 pi over 2, and sine of 1/2, which is the pi over 6 and the 5 pi over 6. So we get all 4 solutions this way. Okay. It's the same problem we're doing the whole time. Yeah. We pull the cosine out. We factored. We factored. They both have a cosine. So cosine came out here, 2 sines left. Cosine came out here, 1's left. Yeah, and that shows us those solutions we are missing. That's the neat part, yeah. Okay? Any other questions before we get to the last one here? Right, you were. There you go. Advanced. Okay, no. All right, guys are doing a good job. Keep asking questions. Keep it up. This is going good. Okay, so even if things is hard, this is going good. Okay, so write an equation which has a solution provided by the x-intercepts of the graph. This is kind of tricky, so I'm just going to kind of show you what they mean, because we don't have any numbers here. We don't know what these equations represent. But if I'm trying to find the intercepts of a graph, that means that f of x times g of x will equal what? No, intercepts. Zero. Intercepts are zeros, right? Intercept is zeros. So what this means is how this works. And I know you kind of wouldn't expect to write it this way. That's why I put it up here. Let me explain how they wrote this. If your f of x is 0, that's an intercept, correct? And then what's 0 times g of x? 0. If your g of x is 0, that's the intercepts for g of x. If that's 0, then the whole thing's 0. So it's a way you can write that gets all intercepts of both functions. So if f of x times g of x is 0, you're finding the solutions or intercepts of those functions. Okay, it's just a way to write it. Now the other way, write an equation which would be an example, or in those terms of f of x and g of x, for their intersection points. So intersection points are points that they what? They have in common, so we simply write it as equals. Okay, you can also write this as that. F of x equals g of x, that's the points they share. Or we can write that as f of x minus g of x. Okay. All right. I know. Okay, so last piece. So they're going to tell you what the graphs are now, and we're going to go from there. Okay, so the graphs in the previous page represent the functions, 3 sine squared x minus 2, g of x is negative cosine 2x. Use a graph calculator to determine the exact roots of the equation. So go ahead and use your calculator to do this part here.